With the first few videos, we learned about the shear and moment diagrams, the sign convention for internal forces and external load that you need to be remember. And then the note for the shear and the note for the moment diagram when you draw from 1 to 4. And that's very important when you draw the moment diagram. In this video, we go to some example for drawing shear and moment diagram. So let's go to example number 1. One here, and like we have a simple support beam. So the left side is pins and the right side is the roller, and in this case I only have one concentrated load in the middle, one concentrated load in the middle, and that 10 pounds. And for the distance of that one, 2 feet and 2 feet. So it's in right in the middle for the 10 pound concentrated load. So from that, how can we draw the shear and moment diagram? First, it's always we find out the external load, external reactions on the support. So this one is simple, 10 pounds. So and it in the middle, right in the middle. So with your good statics, you can find out that one it will be equal to 5 pounds. If you don't know, then of course you go ahead to take a moment about the one side, A or B of the support. So 10, it will be 5, as you can see there. So we always draw the diagram from left to right, and it always start with the shear diagram. Shear diagram. Here, let me write that. For shear diagram from left to right. But exactly the same with the beam here. And the positive and negative, as you can see there, and any change we will have. Okay, so that any roughly change, so from left to right, the first is the support, that's the change. The second point that you may want to consider, that is at the point of the distributed load. And the last one, it will be the external reactions at the roller on the right side of the beam. So how can we have, like I said, start from the left, and it always start at 0. 0 there, and in this case that V, shear V. Okay, and that it will be in pounds. Whatever the load they give us, it will be the same for the shear. So start at 0, and at that point, you see that 5 pounds going up, and 5 pounds going up, that is the external force. Go back to the designer side convention. For external force going up, cause a discontinuity in the internal shear and move up. What does that mean? What does that mean here? It will be in the shear diagram, you will have the discontinuity and move up. So it will be jump from 0, always start with 0. Let's put it in red. 0, go up here, because the force F go up, and it will be plus 5 pounds in there. Cause discontinuity in the shear, start at 0 always, go up 5 pounds because the 5 going up. And then between the left to the middle 10 pounds, no chain, no load, no couple, no distributed load. So what do? Just put that same 5 pound, go there, because no external load or anything change between those two points. And then you will have 10 pounds going down based on the convention that I show up to you for the external load. It go up, then discontinuity internal shear move up. If it go down, then discontinuity in the internal shear and move down. Exactly the same the magnitude. So you will have in this diagram 10 pounds going down, then the discontinuity in the shear diagram and move down. So 10, so go here 5, another 5 will be 10. So as you can see, that have to be -5, and of course the top is +5. +5 go -5, go down 10 total, as you can see. From the middle to the right, nothing, so it will be maintain -5 pounds. And then now the 5 pounds going up at the external support roller on the right side, 5 pounds, exactly the same at the external load. When 5 pounds going up, then cause a discontinuity on the shear, internal shear, move up 5 pounds. So as you can see, it will be stop at 0. So bottom line, if you draw correctly for the shear diagram, then you will start at 0 and then end up at 0. See there? Start at 0 and end up 0 if you draw correctly. If it's not close, then it's something wrong in your diagram. And again, always draw from left to right. Apply that same concept. We draw the moment diagram. So continue here. Moment. Moment here. So moment M, and of course in this case it will be foot-pounds for the unit that with the problem given to us here. So it will be foot-pound. So what we can say from the moment, as you can see, when you draw moment, you look at the shear diagram, the change in moment, area under the shear curve, the slope in the moment of the moment diagram, magnitude of the shear. So what does that mean in here? The area under the shear curve here from left to the middle, these areas, as you can see, equal to 10. Everyone see that, right? 10 foot-pound, 5 times 2 is 10. And of course, the areas from the middle to the right is -10. So with that, we will have the area under the shear curve. So what we have in the note, the change in moment, area under the shear curve, and it always start from 0. And the change in shear, area under the shear curve. So as you can see, you can move from the left to the middle. The shear, the area under the shear curve is 10 foot-pounds. So that equal to the change in shear from the left to the middle. So we can have that is here or there. And it's positive, so it go up. Positive 10, so it go up in there. So from that, as you can see, it will be positive 10 in foot-pounds in the moment diagram when move from left to the middle, because that areas under the shear curve is 10, then that change in the shear from left to the middle, it will be 10. And the slope, as you can see, slope of the moment diagram equal to the magnitude of the shear. Believe it or not, as you can see, that is 10 foot-pounds divided by 2 for the distance from the right to the middle. So 10 divided by 2 equal to 5. Exactly the same, the magnitude of the shear from middle to the from the left to the middle plus 5 in there, as you can see there. So that is the from the left to the middle. And of course, the next one, the change from the middle to the right, the change in the moment diagram equal to the area under the load, the shear curve, area under the shear curve in that middle to the right in negative 10. So it from positive 10 to go to here, it have to be negative 10, go to the right side, so plus 10, negative 10 equal to 0. So as you can see, it go change from this to that point. Have to be equal to negative 10 plus 10, negative 10, so it will be 0. And as you can see there, when you draw correctly from left, you start with 0. Whatever you do, you have to close on the other side, the right side have to be 0. That show you correctly. And slope, as you can see here, this is 2 feet, right? So 10 divided by 2. So that slope here, if you check, that equal to 5 for the shear from left to right. And then negative 5 from the middle to the right. Okay, so that we have for the moment diagram. And for because when you draw with the hand like this, we don't know your line is really straight line or really a parabola or cubic, etc. So for that one, we need to specify the diagram is in that portion is straight line or parabola or cubic. That the maximum we have. So with here, as you can see that is constant, so we can have for the shear here, we should specify that is S, so straight line. So we will not argue, oh, you look like your drawing a curve, not really a straight line, so that put it out. In here, the chain is also straight line. So if it's straight line, put the S on that segment so that we know the line that you draw is straight line. If it's parabola, you put P. If cubic, it means power 3, you will put at C. Make sense? So that you draw for the first example in here. And just plug down here. You can have the positive V on this side, the negative, and similarly, that is positive moment and negative moment. And as you can see, just go talk about the moment. Here, the moment is all from left to right positive, and you can see on top of the horizontal axis there. So what does that mean? It makes sense for yes, because with that 10 pound applied, it creates for the whole beam from left to right tension in the bottom and compression on top, and with that moment it positive. So that's why in that simple support beam you always have a positive moment. And that's shown in the moment diagram. That first example, we have 3 more examples to go.